Hello, this is our sixth group final project, Mendocino motor. First, Mendocino motor uses solar and magnetic power as its power source. We use a solar panel with a 200 turns coil attached to it. When there is a light on solar panel, it will generate current flowing in coil and an electromagnet according to right-hand rule. As a magnet beside this solar panel system, magnet and electromagnet will repel and attract each other. In this way, when we use constant light intensity, fixed distance between solar panel and the magnet, the solar panel will rotate with a constant period. Moreover, since we find that current produced by single solar panel is not enough to rotate continually, we put two solar panels together to get bigger power to rotate. Then, in our realization, we use laser beam, receiver, and LED as our timing gauges. When we provide constant light intensity and fixed distance between magnet and electromagnet, solar panel will keep rotating. When solar panel rotates to block the laser beam, receiver gets no laser beam and off. When laser beam go through solar panel, receiver gets laser beam and on. If receiver on, it will generate a current flow. The current signal will go through transimpedance amplifier and get amplified to activate LED to light. If receiver off, no current will generate and LED dark. In this way, we can find that LED will keep light and dark periodically. We can use it to measure time by counting how many times LED light and dark, and multiply the cycle time by count, and get the measured time. Clock is a machine operating periodically, and Mendocino also works periodically. So that's why we choose Mendocino motor as our final project. Next, if we set different values of light intensity and distance between magnet and electromagnet, we can get different period of LED light and dark. In other words, we can get different clocks with different period in different conditions, depending on one's favor.
Hello. So in this part, I will do some math explanation. The solar panel we use is 0.5 voltage and 230 milliampere. The photo shows that we weld the wire on the panel. Next, I will do some formula in this project. This formula is how to compute the maximum torque. And the second formula is show that how much current the panel can generate. So N is the college of turns, I is the current, and A is the normal of coil of turns, and B is magnetic field. And the second formula showed that the current is depend on how strong the light is. When light is stronger, higher the current is. A practical realization will show this. Let me explain how to compute torque. We take the magnetic field to be uniform over the rectangular loop like this, which has width W and height L. First, we note that the force on the top of and bottom segments are vertical and, therefore, parallel to the shaft, producing no torque. Those vertical forces are equal in magnitude and opposite in direction, so that they also produce no net force on the loop. This photo shows view of the loop from above. Torque is defined as tau equal Rf sine theta, where F is the force, R is the distance from the pivot that the force is applied, and theta is the angle between R and F. As seen in here, it gives the force on the side to be equal and magnitude and opposite in direction, so that the net force is against zero. However, each force produces a clockwise torque. Since R equal W divided by 2, the torque on each vertical segment is Wf sin theta divided 2, like this. And the 2 add to give a total torque, like this. Next, the formula of the current generated by solar panel. By KCL, we can get the formula like this. In simple, if the solar battery in solar panel is ideal, RS is negligible. So the formula can be written as this. The key point of the formula is that the current is dependent on how strong the light is. This is our reference. In this part, I will use Python and LTSpice to do some simulation. First, let me show the Python part. Because the formula we use is to compute torque and current, I want to simulate that if the current is increasing, what will torque change? So, if we make the coil of turns and A cross B as constants, and plot the relation between torque and current, we found that torque is proportional to current, and the current is proportional to how strong the light is. So we can conclude that the cord is proportional to the light. Furthermore, if the light is stronger, the angular speed of the panel will faster. Next, if we make current and A cross B as constants, only change the coil of turns, then we find that if more the coil of turns are, torque is larger. In the project, we use 3 numbers of coils of turns, ensure that more the coil of turns are, the angular speed of the panel will faster. Also, we reuse LT splice to do simulation. This element called optos. It includes both laser and receiver. And this amplifier is OP741, which amplifies the signal received from laser. And we make the resistor 1000, make the signal about 10 times. Because when the panel rotates, the signal like pulse. We make the voltage is pulse and see what the output 2 is. You can see that the output like the pulse. When pulse is on, output 2 also on. When pulse is low, output 2 is also low. What happens if we change the duty cycle of pulse? The result is that output 2 also change. We can change the angular speed of the panel by changing the light, and it acts as changing the duty cycle of pulse.